So in a simple manner, the green chemistry tries to reduce the waste, it tries to reduce the use of materials, reduce the hazard, and also reduce the risk associated in a process, and also it reduces consumption of energy, and finally it reduces the cost of production. So therefore, green chemistry is very important both in academics as well as in industrial production. So whenever we talk about green, there cannot be something arbitrary. So therefore, there are certain parameters to know about a process, how much green it is. And to know that, we use this green matrix. That means there are different terminology what we use to know about how much a reaction is green based on those parameters. One of the example is that is called the yield. Whenever we think about a chemical process, we try to know what is the yield obtained. That means if theoretically if a reaction goes 100%, we are supposed to get the 100% of the product. But in my process, whether I am getting 100%, 30% or whatever the percent. So based on the percent of yield, we can think about a reaction is how successful. Then second thing is that atomic economy. Atomic economy implies that means whenever I do a reaction, then what is the total amount of atoms consumed in the product? You just think about a reaction of addition reaction, where suppose you think about bromination of an alkene. A bromine molecule addition takes place in an alkene, and you end up with a dibromoalkane. That is 100% atom economic process. That means addition reactions are atom economic process because 100% atoms are retained. Now think about the elimination reaction where one molecule goes away, and those reactions are considered as less atom economic process. That means whenever we try to develop reactions, we should also think about the atom economy of a reactions, and we should try to make reactions which are much more atom economic. Similarly, there are various other parameters what we use, like the effective mass yield, that is basically the ratio of the product in kilogram divided by hazardous reagent produced during the process in kilogram multiplied by 100. That is what is known as effective mass yield. Another factor what we frequently use, that is known as E factor. E factor is total amount of waste generated in kilogram divided by the total amount of product in kilogram, and the lesser E factor is better method. Okay, so these are the green metrics which is used to know about how green a process is. Okay. Okay, so now I will discuss about a few recent reactions or the methods what we have developed in our lab. So this work was done by our student, Nurabul Mandal. He is a PMRF student. So you can see, whenever we try to make a method, what I said, that to make a reaction green, we need to think about if I can reduce the number of steps. Because every step, if the number of steps is more, implies your consumption of solvent is also increasing and your cost of production is also increasing. So if I can do a reaction in a single pot, that means in a single pot, instead of going a multi-step, if I can do it in a single step process, that means I can make my reactions greener. So in our lab, we try to design some reactions which are known as multi-component reactions. The reactions where more than two components are added in one pot, and the reactions are designed in such a way that in a successive reactions will go under the same reaction conditions. So what we tried to do in this reaction, if you see, we took the concept of that we wanted to develop a very complex molecule by a very simple phenomena. And what is that concept? The concept is that we wanted to explore, that is called organocatalysis. You know that in our biological system, all reactions are catalyzed by enzymes. And enzymes are nothing but mostly organic molecules. The enzymes are proteins. So we are inspired by the biological processes, and therefore we wanted to explore organic molecule as a catalyst. And in this case, what we used a simple molecule. It is a hexafluoroisopropanol, which is an excellent solvent, and it acts as a hydrogen bonding solvent. So we used hexafluoropropanol, here you can see HFIP, to generate this molecule, and along with that what we used visible light, we used LED light. So in the one pot process, what we have seen, that means you can make your molecules. Initially we just using hexafluoroisopropanol at room temperature. Whenever we take this molecule in one pot, we ended up with a molecule where you can see that thiazole moiety is formed. It's not working. Okay. The thiazole molecule is there and having amino functionality, hydroxycoumarin, this type of interesting, molecular skeletons, and this type of molecules are known as hybrid molecules because the molecule 1 is having more than one pharmacophore. So then we developed this method that how can you generate this molecule where you are generating two rings, one is the benzene ring and another one is the thiazole systems. That means even at room temperature reactions using light as the source of energy and HFIP as the solvent, you can generate this type of very interesting flat molecules where you have the coumarin moiety, where you have naphthalene moiety and a thiazole moiety, and that's the molecule. By seeing the structure you can see it is a complex molecule, but the process of preparation is a very simple method. So that means even at room temperature, without having your sophisticated system, you can develop this type of molecules in a very simple way. And this work recently we have published in Journal of Organic Chemistry, published by American Chemical Society. So it is not that after only we have stopped after preparation, we have also shown that this molecule can be further derivatized, and we have done some reactions and we have done their different derivatives, and we have shown that how the reaction works, what is the role of the light and what is the role of our solvent, that is the HFIP. And we have shown that HFIP acts as a hydrogen bonding catalyst, and light basically is used for the 6-pi electrocyclation reaction, and that is how we end up with a very interesting molecule. So after having this reaction, we have developed another interesting reaction. You can see here that we can make this type of tri-substituted thiazole. Because why I am talking about the thiazole? Because if you see in the literature, you will find that thiazole molecules are prevalent in various different type of drug molecules. They have lot of your medicinal importance. So we wanted to make always hybrid molecules where more than one pharmacophore will be there. In this molecule, if you see that the thiazole is linked with another important molecule that is called indole. So we have prepared a system where you can make this type of tri-substituted thiazole linked with the indole by using one-pot method, and simply you can make the product without going through any involvement of your any catalytic metals or any hazardous conditions. Please go to the later page. Okay, so to make reactions greener, we also use different strategy. Like here I have shown you one strategy. You can see that we can use lemon juice as one of the organic, as one of the solvent for doing your reactions. So what we did in this reaction, if you see that we took these three different substituents, that is a phenyl glycol, that is a ketoaldehyde. You have aminobenzyl thiazoles, and various different interesting molecules, like you can see that you have hydroxycoumarins or N-methyl hydroxyquinoline. In that case, we can get this type of very interesting tricyclic molecules which are having a lot of significance in the medicinal chemistry. And how we did the reaction, you have simply the reaction you can do at room temperature, and you can use lemon juice freshly extracted, and you can use them as a solvent. So that means to make reactions green, we can use various different strategies. I have shown in the first work, if you remember, that we use the strategy of using light as a source of energy. Here we have shown that you can make reactions greener by using a normal extract from your basically lemon juice that can be used as a solvent cum promoter for doing your organic reactions. That means you can make organic reactions by alternative way than whatever the conventional method we do, Because whenever organic reactions comes to our mind, we always think about that means organic solvent has to be used. We always think about some metal catalysis has to be used. It is not necessary always that the reactions, whatever you want to design, that has to be done only using various different type of organic and toxic materials. You can also design reaction in environmental benign manner by using alternative sources. And that is what one of the work that we have shown. So, since time is limited, so you will find that we have published more than 25 works for making various medicinally important molecules using a simple molecule that is known as phenyl glycol. So it is a ketoaldehyde and having a ketone and an aldehyde functionality in the molecule. So it is a 1,2-dicarbonyl molecule, and we have explored this molecule in multi-component reactions. As I told you, the multi-component reactions are the reaction where more than 2 components are added at a time. And we have developed various different methods, and we have published this work in various reputed journals, you can see. And in all the cases, these are the one-pot method. One-pot method implies we have used only in the single flask, and we have not isolated every intermediates and purified. So we have added the starting materials, and finally the products were isolated in very good yield. And for doing this type of reactions, by seeing the outcome, it seems a very easy job because सारा ऐड कर दिया तो कुछ प्रोडक्ट मिल गया, बहुत अच्छा है. But the problem is not that designing reaction, it needs a lot of thoughtful thinking because the molecules, they try to behave differently and you need to bring them, no, you have to come and cooperate. And that is what is the job of the chemist. We need to understand the reactivity, we need to have the understanding about the kinetics, we need to have the understanding about the thermodynamics, and also we need to know at what solvent systems and the proper conditions will be attained, and that is how that is called optimization of the process. So even though if I am showing you one slide that I have developed a method like this, but there are a lot of effort by the students. They do more than 100 reactions to find the optimum condition. So obviously the credit goes to the students, those who are working day and night in our system. And therefore, whatever work I am showing, because of some technical glitches, I have not covered all the things. But mostly if you see, we have done this type of method development where you can generate medicinally important molecules using your one-pot methodology. Apart from this type of work, we also have, can you go with upper slide? Yes. So you can see that we are also working some amount of in the polymer chemistry, so that can be used in detection of various different elements. We developed a method for making coumarin-containing conjugated polymers using simple Suzuki coupling reaction. And this molecule was very interesting because it showed very good fluorescence activity, and even we can also detect mercury and iron ion detection. It can be done from the water system. So you can use as a chemosensor for detecting mercury and iron ion using this type of probes. So we also are working novel materials which can be used for environmental remediation. So these are the different areas where we are working right now. Yeah, please go to the conclusion part. Okay, so finally what we are doing at IIT Patna, so we are trying to develop new methods. We use various different new approaches. Like some of the techniques, what is right now is the hot topics that is known as the CS activation. We are working on the CS activation. We are working on development of new methods using green methods in a one-pot methodology that is called multi-component reactions. We are also working on light-mediated reactions, as I told you, that instead of using a normal conventional heating process where it is a highly energy-consuming process, you can design molecules using your visible light. So we have developed some method using sunlight as the direct source of energy. We also have used some method using some organic molecules as a photocatalyst, which can absorb the light and that can transfer energy to the molecules, and it can be used for making your